Now we're going to move on to a new topic, improper integrals. So let me give you some examples, and then after a while we will take it step by step. So in the past, when we were doing integration, we would always integrate it from one definite point to another definite point. So this wouldn't be infinity; it would be like 7, from one definite point to another definite point. But with improper integrals, we are going to integrate it from 0 all the way to this concept of infinity, all the way to the right here. So we are going to integrate from 0 all the way to infinity. But then you could argue that, well, if you keep on, if you integrate from 0 to infinity, then you're always adding to this area, and then you could always argue that, well, the area is going to we're going to get bigger and bigger and bigger because you're adding each time as you're heading towards infinity. Yes, that will be true if you have a graph of y equals x here. If you keep on adding, if you integrate it from 0 all the way to infinity, then yes, the area will get bigger and bigger and bigger and bigger and bigger. The area will get larger and larger and larger. But that's not true when it comes to this particular graph. For some reason, even though you're adding and adding and adding and adding, the area itself will converge to one particular value. But for y equals x here, even for y equals x here, you're adding and adding and adding. This one here doesn't converge to one particular value. But for some reason, this graph here, it will converge the area, even though you're adding an area, even though you're adding and adding and adding and adding, it will actually converge for some strange reason. Let me give you an example. For example, this number 2 here, I can keep on adding and adding and adding and adding, and it will never get to the number 3. So I can keep on adding, let's say 0.03, and then I can add 0.00007, and I can keep on adding 0.000000009. You see, I can keep on adding and adding and adding, but yet it will never get to the number 3. This is the same analogy here. I can keep on adding to the area. I can keep on adding and adding and adding and adding and adding and adding. But then for some strange reason, this area actually converged to one particular value. So let's try to evaluate this. So the way we would evaluate this would be the way we would evaluate from 0 to infinity would be to do this. Let's just evaluate it to the point B. Okay, so, and then later on, we will allow B to head towards infinity. You see what I mean later. But in order for us to evaluate it from 0 to infinity, we would do this. Let's just evaluate it to this point here, B. Let's just evaluate it from 0 to B. Let's just evaluate it from 0 to B. And then later on, we can take the limit as B tends to infinity. So let's start again here. To evaluate from 0 to infinity, we would let's just say we want to evaluate it to B. So we're going to integrate it from 0 to B. So integrate this, it will then give you this, and we've done this in the past, so you should be able to integrate it by now. So integrate this, it will then give you this from 0 to B. So you would then, you would then put this into here. So that would be this bit here. And then take away, and then put 0 into here. If you put 0 into here, this whole thing here would be 0, and then this whole thing here would be 1, this will be -2. So that would then be this. So now tidy this up, it will then give you this. Don't forget, this is from 0 to B. So if you want to integrate it to let's say 3, to C, then this will be C, and so on. So this is from 0 to B. When you integrate it from 0 to B, it will give you this. Now here's a clever bit. Now let B tend to infinity. So if you let B tend to infinity, then you're taking the limit as B tends to infinity here. So as B tends to infinity, this bit here will head towards 0, and then 0 times 2. So this would be 0. So as B tends to infinity, the whole thing here will be 2. So the whole area will be 2. So hang on. So bear with me. So to integrate it from 0 to infinity, That's really us letting b tend to infinity. So overall the answer would be 2. Okay, so let me just recap. Hang on. So we are trying to integrate it from 0 to infinity, but then to do this we would just say let's evaluate it to the point b here. So let's evaluate it from 0 to b. When you integrate it, we'll then give you this. So b, put b into here and so on. That will then take you to here, and then tidy up. That will then take you to here. So when you integrate it from 0 to b, it will give you this. If you want to integrate it to, let's say, 1 million, take it to 1 million, then this thing here will be 1. So the area would be this 1 million. But then if you want to integrate it from 0 to b, the area would be this. But now you let b tend to infinity. You let b, the clever part's this bit here. You let b tend to infinity. Then this thing here will head towards 0. So this whole thing here will be 2. So overall, you can conclude that from 0 to infinity, the area will be 2. Okay?